Okay, well, everybody, first of all, welcome to section 4.4. Now, you may have noticed that the last video I made was 4.2, and now I'm doing 4.4. And you may think, oh, I forgot, or I'm senile, but no, that's not the. Well, maybe I am, but 4.3 was not forgotten. It's not on the curriculum. It's not part of our curriculum for this course. That's why I didn't do it. Anyway, so we ended 4.2 with some curve sketching, and now the entire 4.4 is going to be getting into curve sketching, just getting some more strategies and sort of like refining our methods, making our methods broader, looking at all kinds of functions, and just kind of like have just a more complete rendition of this fascinating topic. As I mentioned, this is one of my favorite topics in calculus because it's like doing detective work. It's really awesome. But the only thing you have to remember all the time, you just have to remember that we're always switching around. We're looking at the original function, the first derivative function, the second derivative function, and as long as you always bear in mind, you got to keep straight what you're on and what each thing does, then you'll be okay. But if you forget what does what, you're going to it'll just become a whole big mush, become a whole big like stew with just stuff all over the place. So know what you're talking about and be organized, and this will be a zillion times easier. And I'll always be reminding you and pointing things out and trying to make it as clear as possible. I will definitely, so I'm going to now make it as clear as mud. Here we go. Oh boy, okay. So analyze f of x. So, okay, step one is, like we said before, step one of the procedure is all algebra. We want to find the domain of the original function. We want to find the intercepts, and we also want to find the asymptotes, something that we learned how to do in algebra, but I'll show you what I'm talking about over here. So all of step one is basically do all the stuff you did in algebra when you learned this, how to graph functions, and not a stitch of calculus. So in other words, get as much as you can without the calculus before you actually use the calculus. Calculus is a tool, it's an advanced tool, but get all the basic stuff first, the algebra stuff first. Okay, step two is to look at the derivative, the first derivative. And just remember, and of course you find the partition numbers, the critical numbers, blah, blah, blah. And you make a sign chart. And the sign chart is really important because whenever the first derivative is positive, that means the function is increasing. If the first derivative is negative, then it's decreasing. When the first derivative switches from positive to negative or vice versa, that's when you're going to have a local, either maximum or a local minimum. All right, so that's what f prime does. And now step three is to look at f double prime. And so find the partition numbers and make a chart and blah, blah, blah. And just realize that whenever the second derivative is positive, the original curve is concave up. And if the second derivative is negative, the original curve is concave down. And when concavity switches from up to down or vice versa, that's when you have a point of inflection. So here we go. And then finally, sketch the graphs. You're going to put all that together. You're going to draw the asymptotes and the intercepts and the maxims and the mins and the inflections. And you're just going to do everything you have and everything you know, and you're going to put it together to find the sketch. And that's really cool. That's a really cool thing. So let's look at some examples now. So now we're going to do a whole bunch of examples, and it's going to be awesome. So we want to use graphing strategy. We want to use graphing strategy to analyze. So x minus 1. So we're looking at f of x equal to x minus 1 over x minus 2. Now you might remember from algebra. This is it's a hyperbola, but we'll do that step by step. Anyway, so first thing we want to do is we want to look at f itself, the original function, just get the intercepts and the domain and the whole smack. So basically, so the domain is, all I got to do is find the problem numbers. The only problem numbers is x equal 2 because I get a 0 on the bottom of the fraction. So it's all real numbers except x equals 2. So 2 is not part of the domain. That's important to remember that. Everything else is part of the domain. And the y-intercept, well, just plug in x 0 for x, and you get -1. You get -1 over -2, which is 1/2. Now for the x-intercepts, you want to set the fraction equal to 0, but the only way the fraction equals 0 is when the top equals 0. So the x-intercept is when x equals 1. So if x equals 1, and that would be the point 1, 0 is a x-intercept, and 1/2, 0, 1/2 is the y-intercept. And we have the domain, and now there is a horizontal asymptote here, which the horizontal asymptote, again, if you should have done this I'm assuming you did this in algebra, but you take the coefficient of that x and the coefficient of that x and make a fraction, and that's your asymptote. And in that case, it's just 1 over 1, which is 1. So y equals 1 is the horizontal asymptote, and the vertical asymptote is just when I stick in the 2 on the bottom. So the denominator is now vertical asymptote comes because the denominator is 0 and the numerator is not 0. See, if the numerator was also 0, it might not be a vertical asymptote. But if the if the numerator was also 0, it may not. Then you might wind up not having a vertical asymptote. But since the numerator is not 0, if I plug in x equals 2, I get 1 over 0, and that's asymptote time. So x equals 2 is going to be your asymptote, vertical asymptote, and y equals 1 is going to be your horizontal asymptote. Okay, so there we got the asymptotes. Now we want to so that's all the non-calculus. That's just pure graphing and algebra and just stuff that we did before we ever heard of calculus. Now, step 2 is we actually start the calculus. So first we start the calculus with the first derivative, and of course later we're going to look at the calculus with the second derivative. But first things first. So to get the derivative of this original function, it's a quotient, so I'm going to use the quotient rule. So it's x minus 2 times the derivative of the bottom minus x minus 1 times the derivative of the top, x minus 2, the bottom, times the derivative of the top minus the top times the derivative of the bottom, and over the bottom squared, and that just becomes -1 over x minus 2 squared. Now, x minus 2 squared, well, that's a square, and that is always, squares are always positive, but I have a negative square, so it's always going to be negative. The only issue I have is when x equals 2, but x equals 2 is not part of my domain, so don't got to worry about it. Anyway, so it's negative, negative, negative all the way through, which means this function is always decreasing. I can't say it's decreasing when x equals 2 because it's not defined at x equals 2, but it's decreasing from negative infinity all the way up to it, but not including 2, and then from right after 2 all the way to positive infinity. This function is always decreasing, which is weird because it's decreasing. I didn't have that asymptote there, but it's not that hard. Well, we'll see. This is not that hard to put it together. Anyway, let's look at the second derivative. The second derivative is 2 over x minus 2 to the third power. Now, you could do this with quotient rule if you want, because it is a quotient, or you could write this as x minus 2 to the -2 power and use the power rule. Either way, the derivative of this derivative is 2 over x minus 2 to the third. Now, x minus 2 to the third, that could be positive, it could be negative, depending on what's inside the parenthesis. Well, what's inside the parenthesis, well, we're just going to call our partition number is x equal 2. That's inside the parenthesis. And now let's make a sign chart for this. So x minus 2 is negative when x is less than 2, and it's okay, again, a lot of typos here. Wow, I keep all these typos. X minus 2 is negative when x is less than 2, and then it becomes positive when x is greater than 2. Now, notice here, you see these negative signs. That's a typo, and they even here they have it right, concave upward. So it does go from concave down to concave up. Now sketch the graph. So if we just use all the information that we have, we know the asymptotes, we know, here's my asymptotes, we know the intercepts, we know all that stuff, we know the concavity, we know, so basically we could try testing out a few points, blah, blah, blah. And what we wound up having here is, this is as you know, this is hyperbola. So here's one asymptote, there's the other asymptote, that's that asymptote, that's that asymptote. So this is a hyperbola. And we got this with calculus. We didn't need Desmos, we didn't need a graphing calculator. We were able to get this just from, again, plotting about, you notice here we plotted a bunch of points just to get an idea what's happening to this function. And pow, we're in good shape. So yay for us. Okay, let's go on to example 2. X minus 2x minus 1 over x squared. 2x minus 1 over x squared. Let's just take a look. Yeah, okay. Hold on 1 second. Okay, g of x is equal to 2x minus 1 over x squared. A lot of times you see a fraction like this, like to break it up, but for this case, we're better off not breaking it up. So first of all, I see that when x equals 0, that's going to be a out of the domain, and also the top is going to be -1s, which means 0 is going to be an asymptote, a vertical asymptote. When x go, now you may have learned in algebra that when x goes to infinity, that's where you see that's where you see the horizontal asymptotes. And if you have a polynomial on the top and a polynomial on the bottom, but the bottom is a higher degree because the bottom is a second degree polynomial, then the asymptote is just going to be y equals 0. And the domain is everything except for 0, of course. And the x-intercept, well, for the x-intercept, just set this. There's no y-intercept because I can't. Well, y-intercept is when x equals 0, and that's not part of the domain. So there's no y-intercept. But for the x-intercept, set this fraction equal to 0, but the fraction only equals 0 if the top equals 0, which happens when x equals 1/2, 4.5. Now notice the last example was also at 1/2. So that's not necessarily a pattern. That was just a coincidence. Okay, now let's look at the derivative. And to get the now for the derivative, oh, how interesting. Now again, this is a choice. What the book here is doing. Now you could take this whole thing and do a quotient rule. What the textbook chose to do is to split it into 2 fractions, which is what I was talking. It was what I said before I wasn't going to do. But they split it into 2 fractions. And they took each fraction, each derivative individually. Then they put the 2 fractions back together into 1 fraction. So they disassembled it and then they reassembled it, and that's what they got. You could have done this whole problem without splitting it into 2 fractions. You could have done quotient rule and done it that way, but either way, you're going to get you would get the same answer, the same correct answer, which is 2 times 1 minus x over x to the 3rd power. So this is undefined when x equals 0, which is not an issue because that's not part of our domain anyway, and it equals 0 when x equals 1. So the partition numbers for G prime are 0 and 1. The critical numbers of G is x equals 1. Now, notice partition number, okay, and the sign chart for G prime, that's a really important thing, is that it goes from negative to positive and then back to negative, negative, positive, then back to negative. Let me just look at the G prime again. G prime was, G prime. I just want to, yeah, negative, oh, interesting, negative, positive, back to negative. Okay. So, that means that we have, if it's negative positive, that means we have a min at 0, except 0 is not defined, so I can't really, can't really say that. But I have a max at x equals 1. So I have a max at x equals 1. And if I plug 1 in to the original function, I'm going to get 1. So the point of the top of the hill is 1, 1. And again, I can't look at, even though I'm going from negative to positive, it doesn't really count because it's not defined in the middle. So who knows what kind of crazy things happen there. Now let's look at G double prime. So this is G prime. When we split it up, again, taking derivatives, again, it's a choice. The textbook just felt, whoever wrote the textbook felt that it was easier to take separate derivatives and put the fractions back together. You may want to, instead do quotient rule. It's a matter of preference. Either way, they're both correct, and hence you'll get the same correct answer either way. Which one's easier? That's a lot of times it depends on you. Sometimes people say which way is easier. It really depends. Sometimes it depends on your personality. I don't know if that's the right word, but your tendency. What you find easier. Sometimes the problem itself lends itself more to one way than another way. But whether it's easy or hard, it's correct. That's really what I care about. That it's correct, that it's mathematically valid, and it's correct, and that's all that matters. And there are more than one way to do this, so it's mathematically valid and correct. Okay, moving on. So I'm going to get off my soapbox and get to step 3. So this is G prime. So G double prime is this sucker over here. And now if you combine them again into one fraction. Now, why do you want it? Why bother combining it into one fraction? The answer is I could see much more clearly when this thing equals 0 or when it's undefined, when it's combined into one fraction. If it's like this, I can't really tell it's hard to tell by looking at it. When it's like this, I can see right away, if x equals 3/2, that makes it 0. And of course, if x equals 0, that makes it undefined. So those are the partition numbers. And the sign chart is going to be negative, negative, positive, negative, negative, positive, negative, 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 positive, and now to put it all together, this is the crazy thing we get. So we have the horizontal asymptote at x equals 0, the vertical asymptote at the horizontal asymptote at y equals 0, the vertical asymptote on x equals 0, and they both go down like this. It reaches a peak right here at 1, 1. That's the top, and it goes down. Notice that it's concave down here. It's concave down here, and then after x equals 1, that's what becomes concave up. That's kind of cool. It's kind of interesting. And again, even though the derivative went from negative here to positive there, the first derivative, it's still not a min, because it's an asymptote, so it's a whole different. It's all crazy. Anyway, that's it. So we plotted. So using our techniques, we actually plotted this curve. That's fabulous. Okay, let's look at example number 3. We want to look at f of x equals x e to the x, and we want to do the whole smack and graph this sucker, x times e to the x. So now we're getting heavy duty stuff. We're getting to exponential functions. All right. So again, this whole section, this whole section 4.4 is just going into more detail about graphing, curve sketching, they call it. It's using the information from the algebra and the calculus and everything about the original function, the derivative, the second derivative, taking all that information together and using that to sketch the graph. That's really what we're doing here. Okay, well, first of all, f of x equals x e to the x, that has no bad points. The domain is all real numbers. And the y-intercept is if I set this, I have to set this sucker equal to 0. E to the x never equals 0. So the only time this ever equals 0 is when x itself equals 0. And the x-intercept, excuse me, I'm sorry, that's the x-intercept. So 0, and the y-intercept is, if I plug 0 into this, I get 0. So the x-intercept and the y-intercept really wind up being the same point. It's just the origin. The x-intercept and the y-intercept are the same point. It's just, there's really just one intercept here. It's the origin, which happens to intersect both x's. There's no vertical asymptotes, and there's one horizontal asymptote, and that's when x goes to there's one horizontal asymptote, and that's here when x goes to negative infinity. This function goes to 0, which is kind of cool. All right. Anyways, now let's look at that's what we get from just the algebra of it. Now for the calculus of it, let's look at f prime. So f prime, again, I'm going to use product rule here, and I get x e to the x plus e to the x, which is e to the x times x plus 1. So the only time this ever equals 0 is when x equals -1. It's never undefined. So that's my partition number, and there's one critical number, which is x equals -1. So now my sign chart, my sign chart this is weird. Again, I think this is just full of typos, because that -8 should be a -1. So this is anyway, it definitely goes from negative to positive, that's for sure. And it switches at -1, not -8. Again, I'm just pointing out another typo. And we tested with these numbers and pow, that sort of thing. So it's decreasing until it hits -1, then it starts increasing after -1. And the when x equals -1, then I get then y equals -0.37, which is good to know. Alrighty. So now let's look at f double prime. So I have to take the derivative of the derivative, and I get after crunch, gather together like terms, blah blah blah. I get e to the x times x plus 2. That's ultimately what I'm going to get. And we look at the sign chart. We make a sign chart, and it goes again. It also goes from negative to positive. This time it switches at -2. Again, it's a typo here. That should not be -8. Be -2, and it's concave down until it hits -2. Then it becomes concave up at -1. And that, my friend, is the story. And since it changes concavity, that means the -2 is a point of inflection, and the inflection point is -2, -0.27. How do I get -0.27? Just by plugging it in, and that you need a calculator for, to find e to that power. All right, now finally we're going to put all this together, and this is what we get. So we have, now here's our min right there. It's concave up here. Now notice here it's concave down. It's very subtle to see, but it's actually concave. Even though it's being asymptotic to the x-axis, it's concave down. So that's kind of cool. It's kind of interesting the way that works out. And of course, I should have mentioned the min is at -1, and right over here, -2. That's where we have a point of inflection. So it's concave up all the way. It's concave up, concave up, concave up, concave up, concave up till this point. And once you cross that point, it becomes concave down. And again, it's a little subtle to see the concavity, but it is concave down. And now, even though to the eye, it's subtle and difficult to see, but we know it's true because we did the math. When you do that, that's the beauty of doing the math. See, a lot of times when you look at a picture, you look at a graph, you look at a diagram, whatever, it's not always clear from looking at the picture what's going on. But when you crunch out the numbers, when you actually crunch out if you actually see mathematically what's going on. So that's why we like to do both. That's why we look at the pictures, and we look at the numbers behind the pictures. And that really gives us a full understanding and a full knowledge of what's going on. Okay, let's look at example 4. Let f of x equal x squared ln x minus 0.5 x squared. By the way, this little thing over here, this explore and discuss thing, it's about something called L'Hopital's rule. L'Hopital's rule is the section that we skipped. That's 4.3 that we skipped, and it's not part of our curriculum, so I never discussed it. In case you're wondering. Anyway, so let's just move on to example number 4, and we'll go from there. Okay, so now we have f of x is equal to x squared ln x minus 0.5 x squared, and we want to follow the steps and do all our magic. So first, we're going to look at this, no calculus, just algebra, and we want to look at it. So the domain is everything from 0 to infinity, because x squared is always defined, no problem. The only thing that's not defined is when ln is less than or equal to 0, or ln is not positive. Now we're gonna factor this, and we get x squared times ln x minus 0.5. That's important, but we'll get to that in a second. The y-intercept, well, there is no y-intercept because x equals 0 is not part of the domain, so there is no y-intercept. And the x-intercept, you have to set this whole sucker equal to 0. Now, the only time this is going to equal 0 is either if x squared equals 0, which means x equals 0, but that's not part of our domain, so you get that guy. Or ln x minus 0.5 equals 0, which means ln x equals 0.5, which means x is equal to e to the 0.5 power, and that equals, again, you could just crunch that out, whatever that equals. That's some, let's tell you right now what that equals. So E and raised to the 0.5 power, 0.5, and that equals 1.6487, 1.648. And that's going to be what, that's X, that's going to be the X-intercept. Okay, now that was algebra. Now we're going to move on. Oh, I'm sorry, there's one more thing. And yeah, the asymptotes. So one more thing we're gonna squeeze out of the algebra here, and you see that when x goes to we see that when x goes to we see that when x goes to 0, the function just goes to 0, so that's not an asymptote. And we see that when x goes to infinity, the function also just rises up to infinity, so that's not an asymptote either. So we have no vertical asymptotes, no horizontal asymptotes. So that's the way it is, you know, can I say? But there's another kind of asymptote which we're not really dealing with. Something called an oblique asymptote, which we're not really going to deal with. It's not here anyway. But anyway, analyze f prime of x. So f prime, again, I got to take the derivative. So it's x squared times the derivative of ln x plus ln x times the derivative of x squared. That's product rule, minus 0.5 x squared, that's straight power rule. And I do a lot of crunching and canceling and combining like terms. And I just wind up with a very simple, look at this, it's beautiful. This, by the way, this is one of the things I love in math. When you have this whole monstrous, thing here, this whole monstrous expression, and it boils down to something so small and simple, 2x ln x pal. Well, the only time this is ever equal to 0 is if ln is equal to 1. The ln of 1 equals 0, that's always. In fact, the log of 1 equals 0 no matter what the base is. Now for x equal to 0, doesn't matter, it's not part of my domain, so nothing to talk about. And the only critical number of the function f is when x equals 1. Alrighty, whoops. And so we make a sign chart at x equals 1. The function goes from negative to positive, and that means that it goes from decreasing to increasing, so we have a local minimum. And the local minimum is f of 1, which is negative 0.5, so the coordinates of the point is 1 comma negative 0.5. Now let's look at the second derivative. So the second derivative, we get f double prime, I'm sorry, is equal to this whole monster, again, using power rule again, not the power rule, product rule again. And power of this, crunch, 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 crunch. And we get, let's see, 2 plus 2 ln x, and that equals f double prime. I want to set that equal to 0. So that gives us ln x equals negative 1, and that means x would be e to the negative 1. So that's our critical number or partition number, whatever, e to the negative 1. And so which means, so the second derivative, again, by testing some numbers, the second derivative is negative till I hit e to the negative 1, then it becomes positive at that point on, which means the function is going to be the graph of the original function. Again, you see, we're looking at a chart of the second derivative, but this concave up, concave down is referring to the original function, not the derivative functions. Concave down, concave up. And finally, putting this all together, that's our graph. That's a graph right there. So it switches. So we have a minimum, we have a point of inflection, we have, it's not defined, it just goes up forever at that point, and everything is cool and awesome. So there you go. That is our thing. Oh, now remember I said there's something called an oblique asymptote. We weren't going to deal with it yet. So we're looking at it now. An oblique asymptote, well, oblique is like sort of like on a slant. So the asymptote could be vertical, the asymptote could be horizontal, but the asymptote could also be oblique, it could be like slanted. The truth is, there's other kind of asymptotes you could also have. You can actually have a curved asymptote. There's a lot of different kind of asymptotes you could have, but right now we're just looking at straight asymptotes. So if the graph approaches a line that is neither horizontal nor vertical, so we call that, as x approaches plus or minus infinity, then we say that's an oblique asymptote. So let's look at an example of this. Average cost. So here's example 5. It's about average cost. Okay, so we have the cost function C of x equals 5,000 plus 0.5x squared. X is the number of items produced using the graphing. So we want to use a graphing strategy to analyze the graph, find the marginal cost function, and graph it on the same set and so forth. Okay, so the average cost function is when I take the cost function and divide it by x. And so that's going to be 5,000 plus 0.5x squared divided by x, which is 5,000 over x plus 0.5x. The domain of this obviously is everything except for x equaling 0, because that doesn't work. There are no intercepts. I can't have x equals 0, and I can't have y equal 0, and yeah, because the top of this fraction can never equal 0, so there's no intercepts. Now the horizontal asymptote is going to be would be 0.5x, but there's no such thing as 0.5x. That's a horizontal asymptote. So there's no horizontal asymptote. And the vertical asymptote, x equals 0, is a vertical asymptote because the denominator is 0 and the numerator is not 0 if x equals 0. I get 5,000 over 0, so therefore I do have a vertical asymptote. There's also an oblique asymptote, because if x is a large positive number, then 5,000 over x becomes very small. It kind of like disappears, and I'm left with 0.5x. Now 0.5x, like y equals 0.5x, that's a straight line with a slope of 1/2 or 0.5. So that would be the asymptote, the oblique asymptote. So it'll be asymptotic to that line, y equals 0.5x. Now let's look at C bar prime. C bar prime is equal to negative 5,000 over x squared plus 0.5. That's by just taking a straight derivative. Now put this back into one fraction. I get 0.5 x squared minus 5,000 over x squared. I factor the top. I get 0.5 times x minus 100 times x plus 100. So I see that this is going to equal 0. The partition numbers are going to be 0 and 100. Negative 100 doesn't count because I can't have negative numbers in this. And the critical number is going to be 100. So at 100, we have a C prime is 0. It's negative before that and it's positive after that, which means this is a min, because it's decreasing, then it comes up to be increasing. And that's our min of C100. And C100, by the way, if you plug it in, you get 100 into C bar, not C, but C bar, which is C over x. Anyway, the second derivative, that's going to be 10,000 over x cubed, which, that's going to be positive. Again, there's no negative numbers here, so we only have positive numbers, and that's always going to be positive. So this thing is we can't give up the whole way through. And finally, the graph, here's what our graph is going to be. Now, this dotted green line, that's our oblique asymptote. That's y equals 0.5. It's asymptotic to the x-axis, and it's asymptotic to this slanted, sloped green line. And this red line here, that's C prime, which is just equals to x. So there you go. So the marginal cost function is C prime, which is just equal to x. And why is that? Let's remind ourselves what C was. Let's take a look at C. And C was, because the derivative of 5,000 just disappears. This becomes 2 times 0.5 times x, but 2 times 0.5 is just 1, so it's 1x, which is just x. That's why that's 1. And therefore, the minimum average cost occurs when the average cost is equal to the marginal cost, which is kind of cool, right at that point right there, which is kind of interesting. Again, this is business stuff, and but nonetheless, it's interesting. Well, that concludes this section 4.4. Again, one of the most fascinating to me. Every problem here is a detective story, and I'm going through. By the way, I just want to say something. When I make this video, I'm just kind of going through everything, chop. But really, I had to spend time. Looking at this, analyzing, figuring out, working it out. And then I'm giving this whole presentation. But it's a lot of detective work. getting all this information and putting it all together and drawing a picture. And that's really a lot of fun. To me, it's like I feel like I'm Batman or world's greatest detective. I just want to say Sherlock Holmes, whoever. Anyway, that is the end of it. It's been loads of fun. I cannot tell you how much I've enjoyed this, and we'll see you next time. Bye, everybody. Bye.